That was natural language processing 101. So let's look at a specific example. Here, we are going to be looking at a project that aims to identify COVID-19 symptoms in emergency department clinical notes. And we are going to proceed with this project through a software demo. So just to give you a short background for that project, we have clinical notes of patients admitted to ED with suspected COVID-19. So this is, for now, this is a hypothetical scenario, but this is a description of a real ongoing research project that we have at Columbia University. These patients have documented symptoms, but only in the free text ED clinical notes. These are including nursing and physician clinical notes. Now, what remains unclear is what symptoms or symptom clusters are associated with higher risk for COVID-19, right? Very timely question. So the study question is, which symptoms and symptom cluster are associated with higher risk of positive COVID-19 test results? So this is something that we are going to explore in this study. How are we going to do that? We are going to use NimbleMiner, an open source free natural language processing software, to answer the question. This software was developed by my team, so apologize for any inconveniences and things that we are still working on. But basically, how would one access a tool like that? So just by clicking on this link, or copy pasting the link into your web browser, would lead you to a website that will have all the files that you need to run the software, right? So this is basically a folder where the software is. Anybody can go on this website, it's free, publicly available, and you can download the zip of the software. So download the software files on your computer. It is a pretty light load, so it is about 13 megabytes, and you can open those on your computer and see that there is a folder that's called NimbleMiner master. So this is basically the software. Then one would need to read the instructions. So here on the website, we have instructions on how to install the software. I would suggest that you have somebody on the team with some computer skills to install this. On the other hand, if somebody is savvy with software like R or even Stata or SAS, right? Those are common software that we use in research. You are probably going to be able to install this tool. So there are a few specific instructions here about download, right? So download those files on your computer, basically restart the computer, install some of the packages that are needed to run this application, and then open the app. So this is as simple. What will happen when you download the software to your computer, basically? You would see a folder like that with a bunch of files. You only need to click on this file twice, which will basically take you onto a screen like that. So this is an R software. That's how the R software looks like. And you see the code for the application basically presented here. Then one just needs to click Run App, which will present the NimbleMiner software to the user. And this is how the NimbleMiner software looks like. So that's what you would see when you have downloaded and installed the software successfully. Now let's look at the data that is available to us for that. So in terms of data, we have three de-identified clinical notes here, just for the sakes of this demonstration. So these clinical notes, they come from a publicly available database of clinical notes. These are clinical notes from inpatient settings, from hospitals, so ED clinical notes, and they basically they're extracted from a data set, a large publicly available data set called Mimic. And you can see, so looking at those notes, you can see that those are your regular types of clinical notes. So for example, this note has an HPI chief complaint. So there's a description of patient major problem, right? So patient presents with shortness of breath, palpitations, and chest pain. And then there is some more description of patient's condition at the admission to the ED. Patients with history of hypertension, cerebrovascular incident, and a couple of other things, presents to the ED for shortness of breath and some other things, and so on, right? And you can imagine that you would have more, I would imagine that you would have more than 3 clinical notes for something like that. So a worthwhile project would have at least 1,000, possibly more clinical notes. But here is just an example. Now, for each clinical note, you have the result of COVID test, right? So, and here we are talking about we are talking about a specific COVID test that would either have a positive result, so this person had COVID when they were tested in the ED. This person did not have COVID. This person had COVID in the ED. So imagine having a file like that with multiple thousands of patients. That will allow you to answer the clinical questions that we have in mind. So once the application is open, so we are going to go to the first tab of the application, of the NimbleMiner application, and change the category. Basically create a new category that is called shortness, and I like to put underscore, but you don't have to, shortness of breath. So shortness of breath, this is the symptom, so I'm adding this as a category. This is the symptom that we would like to explore in the clinical notes, right? This is the symptom that we would like the system to be able to find in the clinical notes. Now the next important tab here in NimbleMiner is Model Builder. So Model Builder tab basically takes clinical data, and this clinical data should include clinical notes. We have several prepared models, but if you have your own clinical data, this is ideal. So if you have thousands or hundreds of thousands clinical notes, you basically can save them in the folder for NimbleMiner as a file that's called train.txt. So and that's what I did with those de-identified ED nodes. If I go to the folder where NimbleMiner lives, I would look into this folder and see that there is a file that's called there should be a file that's called train. If there is no file called train, then I would create this file by taking the clinical nodes. So basically, this is our file with all the clinical nodes. If there is no train file in the folder, I would save this file into the folder as a text format. So that's what we need for the software to be able to build a training model. And I would save it just as train text, and I would just save it, right? So going back to the folder, we do now have the file that's called train. So basically this train file includes all of our clinical nodes, right, in one file. Now, going back to the software NimbleMiner, what the user is asked to do, so the user is asked to define a couple of parameters here, and you can just keep those set and read the paper that describes our system for further fine-tuning of those parameters. But you can keep them as preset by us. We identified ideal settings for the system. And then the only thing that's needed is to click this button, build word-to-vec model or build glove model. And again, we have more description about the differences between the models in the papers that we published. And we recommend building the first model that's called word-to-vec model. So once this button is clicked, this will basically generate a large model of context and clinical terms associated with specific terms and expressions that one would like to find in the clinical notes. Next, once the model is built, we are going to do the most important part of the job. And here where the user interaction with the system really comes into play. So we are interested in identifying instances of shortness of breath. So as you can see, I'm entering a new expression, right? That would basically indicate when the system would find an expression like that in the text, the system would know that there is a shortness of breath indicated in the text. So I'm entering this first word expression to the system, telling the system that shortness of breath is a symptom that I want to find. The system also gives you an option to explore examples of how this is documented in the clinical notes. So in the 3 clinical notes that we have, some of the examples of shortness of breath are as follows, right? And this might be helpful when you kind of need to see specific examples of how something is documented in the clinical notes. So we looked at this. Now, what I'm going to do, the next important part of the process, part number 2, is to ask the system to basically find words that are similar to this expression shortness of breath based on the model that we developed in step number 1. So that's what I'm doing right now. I'm asking the system to identify 25 expressions that are similar to the word or expression shortness of breath. And these are presented in the tab that's called New Similar Terms, just down below. And you can see this long list of 25 expressions that are basically describing the shortness of breath. These expressions were found automatically, right? So this is how this machine learning artificial intelligence system works, by presenting you with those expressions. The user's job, right? So here where we are, the users and experts in the domain come to play, right? So I usually have nurses, physicians interact with the system. And what I'm asking them to do is basically looking at each one of those examples, right? So in the first column, you have examples of similar terms. So look at this word, basically, or expression, and then indicate whether this word or expression indicates a certain symptom. So here in this case, shortness of breath, we can see that this is a misspelling, right? Shortness of our breath. So this is a misspelling of a shortness of breath. So I would like to keep this expression. Shortness of breath, this is also some type of misspelling. I would like to also keep it in the system. Then we have an expression shortness of, which is not good enough, right? When we just would find shortness of in the text, it won't indicate shortness of breath. So this is, I would not count it as something that I need to select. Then just the shortness, again, palpitations, not related. Then we have dyspnea. So dyspnea, so here the computer was able to automatically suggest this word to us, the word dyspnea, right, which is a shortness of breath. And if we click on examples, we can look at some of the examples in the text. So for example, here, right, shortness of breath with dyspnea and then some other unrelated things. So dyspnea is a relevant example. I would basically click on that and that would enable our system to save it for further iterations. Chest tightness, not relevant. This expression, not relevant. Lightheadedness. Difficulty breathing. Now, that's another nice expression, right, that we would like the system to be able to find. when we are thinking about the symptom of shortness of breath. Then you have somewhat related, but not really exact expressions that will identify shortness of breath, including nausea, vomiting, diarrhea, trouble breathing. That's another nice expression I would include in our further analysis. SOB, shortness of breath, it's a common abbreviation for shortness of breath, right? And the system, again, was able to find it automatically. If you're unsure that this abbreviation works, you can, again, click on examples, and the system would pull a couple of examples from those clinical notes that you have access to of how this is indicated. So you can kind of make sure that this abbreviation, for example, right, indeed refers to shortness of breath. And it does look like it is referring to shortness of breath. So we are at the end of the process of identifying the first list of similar words and expressions, right? So all of those expressions that we identified, they describe shortness of breath. They are synonyms of shortness of breath. I would then click on this button, which will basically save those synonyms for us in the synonym list, right? So those synonyms are going to be added to the one synonym that we already had, so shortness of breath. And then for each one of those synonyms, the system would find examples of other potentially relevant and similar terms, right? So potential synonyms. So the system finished the search. Basically, you can see that those few synonyms that we identified, basically 6 synonyms, were added to the list, right? So you can see the dyspnea, shortness of breath, a couple of misspellings of shortness of breath, difficulty breathing, trouble breathing, shortness of breath abbreviation. They're all in our list right now. And now the system basically presents us with another list of 106 terms that might be potentially similar words or synonyms, basically, to the concept that we want to find in the text. So difficulty breathing, and you can see how the system is good at identifying misspellings, for example. So difficulty breathing, that's some type of misspelling. Then, you have other types of misspellings here. Difficulty breathing, this misspelling, for example, is missing H after T. Difficulty breathing. This expression has some other parts attached to that. And our recommendation is to include those expressions. Then you have an interesting thing, right? So you have an expression that says denies any difficulty breathing. This is not a positive expression that identifies difficulties in breathing. This is basically a negated expression. So that's one of the user tasks, is exclude those expressions from the lists of pre-selected, pre-identified expressions and not include them in our list, basically. Dyspnea is a good expression. Dyspnea, orthopnea, worsening of dyspnea, misspellings of dyspnea, increasing dyspnea, different other types that dyspnea can be misspelled, right? And you can see that dyspnea can be misspelled multiple times. So this is great that we are able to identify all those misspellings automatically. Denies shortness of breath. Again, this is not something we want to include. Here we have the shortness of breath and some other things. So we will keep this expression. Visibly short of breath, denies any shortness of breath, denied. So a couple of those we need to exclude. Shortness of breath, shortness of breath, shortness of breath, trouble breathing. And then, so those are expressions for pre-selected. Basically, we trained the system to be able to identify some of those expressions and pre-select them for the ease of use for us, for the users, right, who are using the system. The system kind of automatically finds those. Now, and then the user's task, basically, right, is to go through this additional list of potential synonyms and basically look at each one of them and decide whether they are relevant synonyms or not. So trouble lying flat, respiratory distress, that's a great one. It's a great expression that, in my mind, describes respiratory, describes trouble breathing. Light, lightheadedness, and fainting, not really related. So some of those expressions you might find related, but I do not think that they're related. And this is why we usually have 2 users that are two expert users that are going through the system and identifying those lists of words to make sure that we do not miss any related words. So again, respiratory distress. So I can see something like tachypnea, which is, very fast breathing. And again, this is decisions made for each specific project. I can decide to include those expressions on the list of synonyms or not, right? So tachypnea, I think here I want to find tachypnea, which is, abnormal breathing, basically. Appearing more dyspneic, we want to see that. And again, we can define that wheezing, for example, will be something that is indicative of shortness of breath, and we will include this or not. That's up to us. The same about orthopnea. So orthopnea, right, the difficulty is some type of difficulty in breathing, but we can decide in consultation with other experts on the team whether to include this or not. I would include it for now. Once the user is done, again, going through the list, right, we have identified 28 terms that are synonyms, and those terms are presented here. I would then ask the system to search to first move those terms to the list of synonyms that we have, and then to search for those terms in the model using machine learning methods, and identify lists of similar words and present those to us, which the system is doing right now. In a few seconds, the system is going to give us a new updated list of potentially similar terms. So the list is ready now. So you can see that we already have 35 expressions that are related to the shortness of breath in a very short time. And then we do have, this new list of potentially similar words and expressions that are related to the shortness of breath, right? So absence of dyspnea, I would exclude that. Progressively more dyspneic, orthopnea, piloorthopnea, denied orthopnea. So like all of those denied and denied, I would exclude those. Otherwise, I might want to exclude something like exertion orthopnea or specific other terms, right, from those lists. But those are basically pre-selected lists of terms, and you can see that the pre-selected blue list of terms that the software was able to identify automatically lasts for a while. And let's say, we finished. So here the user will have to look at some 400 terms. So those new terms, right, to identify any synonyms, basically. But here, let's say that we are finished. Let's imagine that this project was basically over, right? So we save those similar terms as symplins, the ones that we identified. And what we will do at the next step of the system, so those expressions that were just highlighted in blue, they will go and join the list of expressions that we already identified. What will happen next? What the system is able to do next? We are going to just briefly look at this tab that's called Irrelevant Similar Terms Explorer. So this tab basically stores all the expressions that the user or you looked at and identified as irrelevant, right? So and those are useful further down the line when we do further processing of this data. And you can see that those are here. You can move them back to the list of symplins, to the list of synonyms. Sometimes they are related, sometimes they're not related. We do have a negation module that will come handy pretty soon. So what the major goal for the system is to, right now, we are going to take the clinical notes. So the system has a menu, right, to upload the clinical notes. So we have those 3 clinical notes that we looked at before, right? Right now, we are going to ask the system to take those clinical notes. So the system just took it in, and then assign labels. Basically, find the words and expressions related to shortness of breath in those clinical notes. And you can see that, for example, the system was able to find shortness of breath, which is highlighted here. So these are the 3 nodes that we have. The system was able to find shortness of breath and SOB. There are 2 abbreviations that we have in this node, or 2 expressions that we have in this node, right? So chief complaint, patients with shortness of breath, palpitations, and other stuff. And then, there's another mention of this. Then, this note had one mention of shortness of breath. This note, again, had a mention of shortness of breath and dyspnea as well, as you can see, and some other things. So this is what the system is doing, basically. This is what the system is very helpful with. It is generating a set of nodes, clinical nodes that are labeled by the system as having a certain symptom. And if you go to the folder that you store this information in, what you can basically, the system creates a CSV, an Excel file that would have the information in the file. So the file is called positively labeled data. This file would include all the positively labeled data. We can open this file and see that these are our clinical notes that we had. These are some of the previous data that we had, right? So we had COVID test results. We have the label true, which means that we found some expressions related to shortness of breath in these notes. These are the expressions. So shortness of breath and SOB, this is the first node. And then we do have basically categories for shortness of breath, for example. Category, right, has those following expressions found, and this particular node had 2 of those expressions, this particular node had 1, and this particular node had 3 of those expressions. So you can imagine using those files for further analysis, right? So you can have a patient ID here or something like that, and then you will be able to match, basically, to take other characteristics about the patient, so say patient comorbidities, match the patient ID to match the comorbidities by patient ID to the findings of the symptom. And that's how you would create a large data set of labeled clinical nodes. So this, sometimes we end up here. That might be the end goal of the process, to create those large labeled data sets. Some advanced users would go further and conduct machine learning. We would not describe it here in detail, but we do have a module that is aimed at conducting machine learning. So generating further predictive algorithms that will be able to automatically further find expressions like that in the clinical texts. And here, we have some settings for the system. Those settings right now include clearing all previous sampling data, so just, freshen up the system, removing everything. And we do have the log that basically tells you exactly what happened at each point in time, right? So you can see that the log tracks each and every user's action and presents some metrics on systems efficiency. Now, let me show you an example of how this would be used in a larger project. So imagine that for the COVID-19 symptom research, right, we do have the following list of symptoms. These are your commonly reported symptoms of COVID that we identified in the literature. For each one of those symptoms, we developed those vocabularies of terms, right? So we had several clinicians looking and developing vocabularies of terms. We had several clinicians validating that the lists of terms are correct. And this is the final result. You can see, for example, that for the category of shortness of breath, we have about 636 expressions. Those expressions include, here are some of the examples, right? So those examples include shortness of breath. Some of the following examples include orthopnea. Again, shortness, lots of shortness of breath, dyspnea, acutely dyspneic. So different types of expressions like that, and we have those for all of the categories, right? And here we wanted to find, for example, all the instances of nausea, and you can see that for the nausea category, we have 435 expressions, including abdominal pain nausea, right? Abdominal pain, V, so those NV indicates nausea and vomiting, right? It's a common abbreviation. Here it got all stuck together, and that's what we want the system to be able to find. Now, let's use this vocabulary, apply this vocabulary on the nodes that we have, on the clinical nodes that we have. What the result would be basically, right? So now each one of those 3 nodes that we have was labeled for presence of all the COVID-19 symptoms. And you can see that all of those 19 COVID-19 symptoms. So you can see that, for example, here the system was able to find shortness of breath for this patient. And then we also, one of the other categories was chest pain, right? And, you know, shortness of breath was here as well. This patient has coughing as well. But then you can see some of the things that are highlighted in red. So denies any nausea and vomiting in our case, and abdominal pain. These were some of the symptoms. These were some of the similar expressions that we included in this work, some of the categories. So you can see that the system was able to identify that the patient denies those symptoms, right? Or, you know, again, patient has fatigue, so positive for fatigue, but negative for activity change, and so on, for chills and fever, right? And you can see that, you know, in another note, right, again, you know, patient presents with a bunch of symptoms that we have here, but denies chest pain, headache, and vomiting, right? And we were able to identify this. So, you know, not on file. So you can see that the system was kind of accurately defining negations. And we do have a list of negations that we are using. Those negations can come before or after the expression. And here we have the distance between the negation and specific similar word that the users can kind of define here. And sometimes it is useful, but this is like a further advanced training for the system. Now, let's look at the results of this again. So the result of this work will be again, you know, so we have the 3 clinical nodes that we wanted to label for presence of symptoms. And right now, you know, you see this list of 19 COVID symptoms. Each one indicated, again, you know, shortness of breath. We already saw that, right? So this is the category of shortness of breath. But then, for example, chest pain, right? So there was an indication of chest pain in this note, clinical note number 1. There was an indication of mechanical fall or syncope in another note here. There was an indication of fatigue, basically, in 2 of the nodes. So note number 1 and note number 3 appeared lethargic and was fatigued. So you can imagine merging all of those back to the main file that you would have on those patients. And this concludes our description of the NimbleMiner system. Please feel free to download and use the system. Reach out if you have any questions. And happy to share any vocabularies that you think are relevant for your work. We can talk about that further if you email me personally. Thank you. So here are a couple of concluding thoughts for today. Let's talk about natural language processing evaluation. The main question of evaluating your natural language processing algorithm is how accurate is your NLP system? So in order to understand that, and we briefly mentioned that not all the nursing NLP studies are doing this system evaluation, which is very important because without evaluation, we don't know how accurately the system would identify the concepts it needs to identify. So the steps of the process are as follows. The first step is to generate a gold standard, ground truth random subset of clinical notes reviewed by clinical experts. Let's take an example. What my team is usually doing, we are taking 2 registered nurses, right, or physicians for some cases. For some cases, these are research assistants or students. So, for example, we take 2 registered nurses experienced in the ED to read a sample of 500 clinical notes. And that follows the idea of the COVID-19 project. For each note, we would ask the nurse, right? We would ask the human expert reviewer to indicate whether shortness of breath is present or not. And an example would be, you can see an example of the note on the screen, HPI chief complaint, patient presents with shortness of breath, fever, dizziness, syncope. So in this case, both of the nurses would probably say yes to the question whether there is a shortness of breath described in this note, because it's clearly indicated. That's another example where both of the nurses would likely say no, because there is a clear indication of no SOB, no shortness of breath for this patient. At step number 2, you apply your natural language processing system on the gold standard and calculate the following metrics. So it is important to calculate the precision, the number of true positives out of the total number of predicted positives, recall, number of true positives out of actual number of positives, and then F-score. F-score is a harmonic weighted mean of the precision and recall. So in general, an F measure of higher than 0.8 or 80% would indicate a well-balanced and functioning system. F measure, like all the other metrics like precision and recall, varies between 0 and 1, with higher numbers indicating better performance. A couple of words about natural language processing self-learning resources. So we're lucky to live in the age where a variety of learning, self-learning resources exist out there. That's one website. It is called Coursera. So this website basically will have a variety of massive open online courses, books, right, that you can take, some for free. Most of the courses you can audit for free, which basically means that you don't get to do homework, but you can watch all the videos and you can interact with all the course assignments, but you won't get a certificate if you don't pay something like between $30 and $50. So the pay is not high for each course. This is a very nice specialization on Coursera. This specialization in natural language processing would include 4 courses focused on different types of natural language processing, mostly machine learning based natural language processing. So nice specialization. I have a link here. That's another type of, it's a separate course on machine learning, again on the same platform, Coursera. So applied text mining in Python. So for this course, a person who will take this course will probably need some basic knowledge in coding, right? So in Python specifically. So that might be of interest to some. My favorite, although not specifically text mining, but that's what some of my students are doing, is this course from the UC San Diego. The course is called Code-Free Data Science. And in this course, you will learn the software, freely available, again, open source software, very easy to use, that doesn't require any coding. And the software basically allows you to do natural language processing, so a lot of natural language processing types, from rule-based systems to machine learning systems, and also implement other types of machine learning. So in summary, today we learned about different NLP natural language processing examples, including self-management status, wound information, prediction of emergency department and hospitalizations. We learned about the futuristic trends such as speech recognition. We briefly looked at the results of natural language processing integrative literature review, and we saw that there is an emerging body of research on natural language processing in nursing, and we hope to see this trend going forward. We also looked at the software demo, NimbleMiner, and you have all the link and all the knowledge to be able to use the software. So let's move on to the questions and answers. I would like to thank the National Institute of Nursing Research for this great initiative on advanced data science methods and artificial intelligence overall. This is my contact information here on the slide, and please feel free to contact me at any time with any types of questions you might have on the natural language processing. Thank you.